In this video, we're going to compute the block shear strength of a tension member system. In this problem, we're specifically going to calculate two different block shear values, one for this gusset and one for this bar. We're told that both members are made out of A36 steel. The gusset is 5/8 of an inch thick. We have a 7 by 1/2 inch bar, and the connection is made of 1/2 inch bolts. We have two factors here that I'm giving right in the beginning because we're going to compute the LRFD and the ASD strengths of these members. Before we fully get into this, though, we should discuss what is block shear. Well, block shear is essentially saying that when we have a connection as shown here, we have to analyze whether this section will completely tear out from the member, and this is called block shear. So we have two shear failure planes and one tension failure plane in this problem specifically. You could have different configurations of this depending on how many rows of bolts you have, but this is essentially how the idea works. And the same thing is going to happen for the gusset. If we have a gusset that looks like this with holes here, 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 and here, we're essentially looking for the same failure. It's the same type. And we're going to check both the gusset and the bar in this problem to ensure that the connection is good for block shear. Block shear is governed by this AISC equation right here. It's J4-5. I know it looks pretty long, but it's set up as an inequality because this over here on the right is set as the upper limit for this. So essentially, this on the right is a limiting factor for what the AISC developed equation is. So in this problem, we have a couple of things that we can knock out right off the bat, because these are going to be the same for all cases of block shear for the bar, and the gusset we'll have to calculate separately. So UBS, which is shown here, is the shear lag factor for block shear, and there's only two different values it could be. The other possible value is UBS equals 0.5, but that only really applies to specific cases like some very specifically coped beams, which is not what we're dealing with here. We're dealing with two pieces of flat bar / plate. Since we're dealing with A36 steel, we can say that we have 58 KSI, and then we have these three variables here. And actually, I realized just now that I miswrote one of those. This is supposed to be ANT, not ANB. But same thing is still holding true, okay? We have ANV, which is our net shear area. We have AGV, which is our gross shear area. And ANT, which is our net tension area. So with these three things, we can actually calculate these before we start doing the full problem. It's going to save us some time, because ANV, AGV, and ANT will be the same for the bar, and they'll be the same for the gusset, so we can calculate them separately. So our net shear area is going to be related to our net area. If you remember doing this from a more basic tension problem using yielding or rupture, we have the gross area minus this sum of the diameters times the thicknesses. But if we look at block shear, we actually have to consider that when we're breaking across this plane right here, or across this plane right here, we're cutting one of these holes in half. So actually, for either of these cases, we have, for shear, our net shear area, we have 1.5 holes because we're splitting it across the one. So net shear area, we have AG. Mind you, there's two of these shear planes. We have shear 1 and shear 2. So we have 2 times the gross area minus the sum of the diameters times the thicknesses, which is 1.5 times diameter of the hole times the thickness of the hole. That's going to be 2 times our gross area. It is a 7 inch by 1/2 inch bar. And we have 1.5 holes that are going to be, that is a 1/2 inch bolt plus 1/16 for roughness, plus 1/16 for spacing, and then another 1/2 inch because we're dealing with thickness here. So we can calculate this out real quickly. We have 2 times the quantity, 3.5 minus 1.5 times, that's going to be a 5/8 hole, times a 1/2 inch thickness. And we have 6.0625 inches squared. Now if we want to do our gross area, this is, oh, you know what? I actually did something wrong here. When we're looking at this, our gross area is actually not the gross area of the plate. See, this is a common mistake that can be made. We're actually looking at the gross area along this plane right here. So if we look at the dimensions that are up here, we have 5 inches. That's a 5-inch length times a 1/2 inch thickness. So that's my apologies. That's my bad. But yeah, that's a very careful thing. That's a very important thing to be looking at. Your gross area is not the same as the gross area of your plate. That's actually 4.0625 inches squared. Now our gross area is just going to be 2 times that area gross, right? That part's not too difficult. So that's 2 times 5 inches times a 1/2 inch. And you are going to get, quite predictably here, 2 times 5 times 0.5, 5 inches, right? Because the 2 and the 1/2 inch will cancel. This is inches squared. Now our net tension area, we're going to have to apply similar principles. So we have to care about what is this spacing here, and then we're going to have to subtract 2 half bolt holes, which is going to be 1 bolt hole. So we only have 1 surface here, and our assumed area would be 4 inches, because that's the spacing, times a 1/2 inch. Now we have to subtract, we'll say 2 1/2 of a bolt holes, and then we're going to do 1/2 inch plus 16th plus 16th. We don't have to write that out again. That's 5/8 of an inch times 1/2 is the thickness of your plate. And with this, we should be able to get our net tension area. And if you just want to do a unit check for sanity, it's going to be inches squared, unitless, unitless. Then we have inches, and this is inches as well. So you're all good. This is going to be an inches squared. So we have 1 times 2 minus, that's 1 times 5/8 times 1/2. So just simplifying this so you can put it in your calculator. 2 minus 5/8 times a 1/2 inch. You get 1.6875. So are we done with calculating the areas? Not quite, right? Because now we have our values for the bar, but we don't have our gusset values yet. So we're going to do those. Let's do our gusset calculations. So we're going to calculate the exact same things. We need we'll switch the order of this time. We'll do AGV, ANV, and ANT. With these values, we'll have what we need to start plugging into these equations. So, if we're looking at our gusset, we'll see that we have slightly different spacing and that we also have a 5/8 inch angle. Now, the bolt holes are going to be exactly the same because we're still dealing with a 1/2 inch bolt, and therefore we're still going to have to calculate the 16th plus the 16th gives us a 5/8 hole. But the 3 inches is important, and this will remain as 4 inches. So our gross area of shear is going to be equal to, once again, 2 times 6 inches of connection, because it was 3 inches and 3 inches. I'll write it as that. 3 inches plus 3 inches times a 5/8 plate. And that will give you 2 times 6 times 5/8. That gives you 7.5 inches squared of gross area. Now we can come down here, start doing our net. We have our gross area of shear. We already did it. Is 7.5 inches squared. Well, I actually shouldn't do it like that. We'll do it this way again. So 6 inches of connection times 5/8 of an inch, because that's technically the correct way to do this. Then once again, we're going to have 2 different bolt holes at, 1.5 bolt holes multiplied by 5/8 of an inch times 5/8 of an inch again, because we're dealing with the thickness of the material is 5/8. So sanity check, inches squared, we should be good. Especially if ANV needs to come out smaller than AGV. So 2 times the quantity 6 times 5/8 minus 1.5 times 5/8 times 5/8. And see, I forgot my decimal in my calculator, so it came out as a negative number, and we know that's not right. So our correct answer is 6.33 inches squared for our gross area. Now if we go to do the tension, we're going to do the same thing we did last time. We only have one failure plan. It is a 4-inch connection times a 5/8 inch thickness of material, minus 2 times 0.5 bolt holes, because we have those two connections. Then we have a bolt diameter of 5/8 of an inch, or a hole diameter of 5/8 of an inch, and a material of 5/8 of an inch. Close all that off. 4 times 5/8 minus 2 times 0.5 is 1 times, or pardon me, this is a minus now, minus 5/8 squared, essentially, gives us 2.422 inches squared. So from the principle of using areas, we could effectively look at this and say that because all of the values for the gusset are smaller, the gusset will not govern, and that the bar will be governing because it has less net and gross area. And that's a fair thing to say. If you look at all of these calculations, it's true. So we can rule out the gusset governing the equation, and we can now start to actually go forward with AISC J4-5. So I'm going to copy this down here so that I don't have to write it all right now. But we're going to go through and analyze this. We're going to have to make 2 different calculation groups, and then we'll be able to apply our factored loads once we get Rn. So the first thing we're going to do is we're going to take this left equation, we're going to plug into that. So we have Rn is equal to 0.6 FU ANV plus UBS FU ANT. And we've now calculated all of this, so it becomes a little bit easier. 0.6 times 58 times a value of ANV equals 4.0625 plus 1.0, because our UBS factor is 1.0. FU is 58 again, and T is 1.6875. So plug this into our calculator, and we will get 4.65 plus 1.0 times 58 times 1.6875, 239.25, and this is in kips. And easy way to remember, or just go through it, KSI inches squared. This is the same thing again, KSI inches squared. Those units will cancel off and give you kips. So now for the part 2 of this, 0.6 FY AGV plus UBS FU ANT. 0.6, we're dealing with 36 KSI material. Our gross area of shear is 5 inches squared. I don't know why I wrote the units in there. I haven't been doing that for the rest. Try to be consistent when you do that. It'll save your sanity. 58. And then this second part of the equation here has not changed from this. So we're going to get the same value for that part of the equation. And now, same thing again, just plug it in. And you're going to find that you get 205.875. So, as I mentioned near the beginning of this, you're dealing with an upper limit of this second equation that we just did right here. So since that right side of the equation is larger, our upper limit is going to be Rn is equal to 205.875 kips. Essentially, whichever one of those two values is smaller, that's what you're going to end up choosing. So now we can go into ASD and LRFD. I gave you the equations up near the top, or the resistance factors in the beginning of this problem. We'll just take them and copy them down real quick. And if we're going to just do this really quickly. Oops, that didn't need to copy. For ASD, all we're going to do is we're going to take Pn and divide it by or for this case, Rn, and divide it by this. We're going to get 205.875 divided by 2. And we'll take that. You get 102.9375 is the allowable strength for ASD. If we're going to do LRFD, we can go through and we'll say that our value is going to be phi t. I'll write this properly. Ru would have to be less than phi t Rn. And with this, we'll have 0.75 times 205.875, because remember that Rn, that nominal strength value, is not a factor of the like the design methodology that you're using. It is 100% just based off the member properties, at least for this type of equation. So your sum of the factored loads for LRFD would have to be less than or equal to 154.41 kips, and for ASD, your allowable strength is 102.937. So I hope this was helpful to you. I know we didn't really go through the gusset specifically. We kind of analyzed it, but we determined that it wouldn't fail, and you can take these values and you would plug them in exactly the same way into this equation right here, and you'd be able to find the strength of the gusset. But we know that that is not going to be governing the equation, so we didn't really have to worry about it. So I hope you found this helpful. If you did, stay tuned. There's more to come. Thank you.